Hi folks. We've looked at doing simple subtraction problems for calculating heat if we're given a reaction pathway diagram, but how do scientists even get those numbers for the reaction pathway diagram? We're going to look at how to calculate heat from experimental values. But before we do that, I want to just walk you through a little bit of a thought exercise here. Which takes more energy to heat? Less water that we're heating up by 5 degrees Celsius or more water that we're heating up by 5 degrees Celsius? I hope you said this one. Here's another thought exercise. Which takes more energy to heat? I've got equal water in both glasses, but this one I want to heat up by 5 degrees Celsius, and this one I want to heat up by 75 degrees Celsius. I hope you said this one. One last thought exercise for you. Which takes more energy to heat? A glass of water or a glass of air that you're trying to heat up by 5 degrees? This one might be a little less familiar to you, but water does take more energy to heat than air does. This is why if it's been cold overnight but then warm the next day and you want to go swimming, the water temperature does not heat up nearly as fast as the air temperature does. So sometimes it can feel very chilly jumping into a pool if it's been cold overnight. So how do we calculate heat? Remember, heat cannot be measured directly. We have to calculate it. And heat transfer depends on 3 different things, which you've actually just thought about. Thing number 1, what is the material? Different materials have different specific heat capacities. And I'll talk about what specific heat capacity means in a minute, but what material you're using matters. Number 2, what is the mass of the material? You guys told me that a smaller cup would take less energy to heat than a bigger cup of water. Lastly, the size of the temperature change. If you want to heat a material up a lot, it takes more energy than just heating it up a little. Specific heat capacity. Specific heat capacity is a way of putting a number on how much energy it takes to heat up a particular substance. So the definition of specific heat capacity is it's the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So each different substance has its own specific heat capacity because each substance is different. The units for specific heat capacity are joules per gram degree Celsius or joules per gram degree Kelvin. A calorimeter is a piece of equipment that scientists use to determine the quantity of heat absorbed or released in a chemical or physical change. Remember, we need to measure temperature changes because heat cannot be measured directly. So we're using temperature change to help us do our calculations. And these pieces of equipment are generally insulated well, like using styrofoam cups to keep the temperature from changing except due to the reaction or the physical change that is being studied. This is a bomb calorimeter. It's used to measure like food calories. Calorie content of foods, and this is more the kind of calorimeter that you would see in a high school lab. Okay, I told you that calculating heat depended on specific heat capacity, mass, and temperature change. This is the equation that lets us calculate heat. So let's talk about what each of these symbols mean. Q equals C times M times delta T. Q stands for heat. The units are joules. CP stands for specific heat capacity. Those units, I already gave them to you, but they're joules per grams degree Celsius or joules per grams Kelvin. M stands for mass. And you remember from Module 0 that the units for mass are grams. And delta T. That delta symbol, that triangle, it's a Greek letter delta, and it means change. So delta T means change in temperature. The units can be degrees Celsius or Kelvin. Delta T is always going to be the final temperature minus the initial temperature. final minus initial. The order does matter because the order is going to give you the correct sign for your final Q value. Remember, we want a negative Q value if it's exothermic and a positive Q value if it's endothermic. So let's look at an example on how to use this heat equation. Calculate the heat change when 895 grams of iron cools from 75 degrees to 45 degrees. And we're also given the specific heat of iron. So what am I being asked for here? I'm being asked to calculate the heat change. That is Q. I'm being asked to calculate Q. I know that Q equals C times M times delta T. So that is the equation I'm going to need to use. I just need to figure out what my other values are. 895 grams. Grams are the units for mass. So I'm going to label this number with the symbol that I'm going to use in my equation. That's my mass. Iron cools from 75 degrees to 45 degrees. This is the information I need for my delta T, but my delta T isn't actually given to me. I have to do the calculation. So delta T is the final minus the initial. So it's going to be 45 minus 75. So that is going to be negative 30. I'm going to put a decimal point there because that 0 is significant. These two numbers had values in the ones place, so they were accurate to the ones place. So my subtraction answer needs to be significant to the ones place as well. Specific heat of iron, this is the CP value. This is the specific heat capacity. So when I plug these values into my equation, I'm going to use 0.449 joules per gram degree Celsius times my mass, which is 895 grams, times my delta T, which is going to be negative 30 degrees Celsius. Notice my degrees Celsius units cancel out, my grams units cancel out, and the only units I'm left with are going to be joules, which is good because I'm calculating a heat change, which is an energy change, and units for energy are joules. So looking at the units can help you check to make sure that you've set up the equation correctly. Now I just need to multiply these numbers in my calculator, and when I type all that in my calculator, I get negative 12,055.65. Goes on. So remember from Module 0 about significant figures. Whenever you do a math problem, you should consider your significant figures before you move on from the problem. In this example, in this multiplication problem, I have 3 sig figs, 3 sig figs, 2 sig figs. In a multiplication problem, the number of sig figs you have in your final answer is limited by whichever value in your multiplication division problem had the fewest sig figs, and that's this guy here, 2 significant figures. So my final answer can only be reported to 2 significant figures. That's rounding off my number here. So my final answer is negative 12,000 joules. Another example. A 4-gram sample of glass was heated from 274 K to 314 K and was found to have absorbed 32 joules of energy as heat. So I'm given a mass. I'm given information to calculate a temperature change, which will be 40 K. And I'm given a Q value. I'm given an energy in joules, which is how I know this is Q. What is the specific heat capacity for this type of glass? I'm trying to calculate CP. So with my equation, Q equals C times M times delta T, I want to solve for C. C is being multiplied by M and delta T, so I want to divide those away. Divide away the M, divide away the delta T. But if I do that to the right side of the equation, I need to do that to the left side of the equation as well. The M goes away because I divided it away. The delta T goes away because I divided it away. And I'm left with the equation C equals Q divided by M times delta T. So I'm going to go ahead and fill in the values here. My Q value is 32 joules. My mass is 4.0 grams. And my delta T is 40 Kelvin. If I do the math, I will get the answer 0.2 on my calculator. And when I look at my units, I see that my units are joules per gram per Kelvin. Joules over grams and Kelvin. So by putting the units in the correct place in the problem, it actually gave me the correct units at the end. Students are sometimes confused by the units for specific heat capacity, but if you plug it in correctly into your equation, you'll get the correct units at the end. Remember, I said that checking for significant figures is always important, so let's see if my sig figs are okay. I've got 2 sig figs up top, 2 sig figs here, 2 sig figs here. So my answer should have 2 significant figures. Right now, my answer only has 1 significant figure. I need to add in a second significant digit in order for my answer to have the right level of precision. Let's look at the next example. Calculate how much heat I'm calculating Q. 32 grams, this is my mass, of water absorbs when heated from 25 to 80 degrees Celsius. This is going to give me information for my delta T. I need to do 80 minus 25 is 55 degrees Celsius. And I'm given the specific heat of water, CP. All right, I need to calculate Q, but I know my CP, my M, and my delta T. So that's fine. Q equals C times M times delta T. So I plug in the values, 4.18 joules per gram degree Celsius times my mass, which is 32.0 grams, times my delta T, which is 55 degrees Celsius. Grams cancels out, degrees Celsius cancels out. I'm left with joules. And according to my calculator, I'm going to get an answer like 7,356.8 joules. But significant figures, 3 sig figs, 3 sig figs, 2 sig figs. This is my limiting value in terms of determining my sig figs. So I have to round off to 1, 2 significant digits. I need to round off here. So my final answer will be 7,400, because this number is 5 or higher, I need to round up. But I add in these non-significant zeros as placeholders because this is in the 7,000s. I'm not trying to round this value off to 74. That would be a completely different value. 7,400 joules. One more example. A 28.2 gram sample. That's a mass right there. Grams indicate mass. Of iron requires 260 joules. That's an energy. That's going to be my Q value. Joules are units for energy. To raise the temperature from 20 to 40 degrees Celsius. This is the information I need for my delta T. Delta T is final minus initial. 40 minus 20 is 20 degrees Celsius. What is the specific heat of the iron? This is what I need to calculate for, CP. Okay, again, my base equation is Q equals C times M times delta T, But just like we did with question 2, we can divide away the m and the delta T on both sides of the equation so that we get C all by itself. The equation we're going to use is Q divided by M and the delta T. So my Q value is 260 joules. My M value is 28.2 grams. And my delta T value is 20 degrees Celsius. And my calculator gives me an answer like 0.46099, but of course I have to think about significant figures. I have 2 sig figs here, 3 here, and 2 here. So my final answer has to have 2 significant figures, which will be 0.46. And of course I need units. Joules divided by grams degrees Celsius. Joules divided by grams degrees Celsius is my final answer. I hope this helped.